is always increasing on a certain interval, the function is concave up. Yep. So let's look at this. Let's just make up some numbers. Is that okay? All right, let's go on. We're going to just make up some slopes. It won't have to be perfect. What would be the slope of this line right here? Let's just make, how about m equals -2? Will that work, everyone? Remember, m is f prime. You all agree? All right, here's some function, but the slope of the tangent line right there is -2. It's kind of steep. Now, right here, I moved a little bit further. The slope's not as steep, but it's still negative. Do you agree? Okay, so the slope is -1. Will that work? Like, well, it's not as steep. I'm making these up. But yeah, it's like, okay, it's not as steep as that. It's like -1. And that's f prime, right? But do you agree as it went from here to here, didn't the slope actually increase?
Increase, yeah.
-2 to -1 means it got higher, right? It increased, okay. And then what's the slope right there? I bet you all know.
0.
So f prime would equal 0. And let's just pick above, how about right there? What's f prime right there?
1.
1. And then way up here was getting steep. We can just say, all right, maybe slope got up to like a 2. But over this entire interval here, of this cup, we said the slope of the tangent line kept increasing. Notice we didn't say the word positive or negative though. That's the definition of concave up. A function is concave up, all right? As long as the slope of the tangent line drawn in the curve is increasing along that interval. If the first derivative is increasing. We put that into words, it sounds all complicated, and when I think images tell the story. So that's what I mean, like, if you're like, I'm not going to confuse this. I can just draw a cup, maybe do this, along my cup, and I understand what concave up means, right? Function's concave up. What's concave down mean? It means the slope is always doing what?
Decreasing.
So I'm going to make up some slopes, okay? M is -2, M is -1, M is 0 here. Maybe over here, M is 1. Oh, let me get these right. Sorry about that. Everyone's like, what are you doing? 2, 1, 0. Now the slope would be what?
Negative.
Negative.
1.
And then right here. And remember, these are first derivatives. First derivative at that location. First derivative. First derivative. M for slope, first derivative. What happened with these slopes? They kept decreasing when it was concave down. Cool? So you can always define it if you want. You're like, okay, I know what it means. For a function to be concave down, that means the first derivative is always, I don't say positive or negative, I say the first derivative is always decreasing. But the summary of all this is really these images. It's really these images. The upside down frown and the concave up. Go ahead, Josephine.
Do you always take it from left to right?
Yep, very good. We always read graphs from left to right. We always describe graphs from left to right. Outstanding. Because if we didn't do that, you get totally flip-flop answers. Very good. Everything in mathematics, we describe left to right, we write intervals from left to right. Or if you want, you could say we do everything from lowest to highest. And then you got range taken care of. Okay? Very good. Hey, so I'm going to draw an image. I wonder if you all could tell me where it went concave up, where it went concave down. Can I erase these? Yeah, there we go. Get some graph. I just want to make some kind of function like that. All right. What's it doing right here? Very good, it's decreasing. Is it concave up or concave down? So you got to think of the cup. Ooh, good. It's like the cup part. So I'll just put a CU right here, right? It's like concave up, isn't it? Now somewhere around what? See, I see in here, I see it's concave down. So somewhere between here and then here, it turned into what? Concave down. It probably occurred what? Perhaps maybe halfway between this and this? We don't know precisely right now.
On the left
We
side,
can do
how do you get the that's decreasing, right? Concave up. On the other side is this.
That's right. And so a function can be concave up,
Uh huh.
but the first derivative could be negative. That's it, because remember, the whole idea of concave up means the slope of the tangent line or the first derivative is always increasing.
So is this the first derivative, the function that you drew?
Good question, Art. This would be f.
Okay.
So if this was f, everyone, this function that I drew, this is f. We could say f is concave up from about here to here, and then stop. And then right about here, it turned into what?
Concave down.
Concave down, just about, roughly. You go, wait, how do we find that point exactly? That's what we're gonna talk about. We'll precisely find that value, true? And then right about here, concave down, and then after here, it went back to what?
Concave up.
So it looks like this function here was concave up from about here to here, then it went concave down, then it changed to what? Concave up. So there's got to be a name for a point where a function changes concavity. And there's a name for it. And it's called a point of inflection. So how many points of inflection do you see?
1, 2, 3.
There's two of them, aren't there?
Yeah.
Now if you want to write POI for point of inflection. So definition of a point of inflection? A point of inflection is a point such that the function changes what?
Concavity.
That's the definition. You can call it a POI, a POI. I have some students who go, no, even better, I'll call it IP for inflection point. So what do you prefer? Because you'll probably label these things when you're doing your math. You want to call them POIs, point of inflection? Or do you want to call them IP, inflection points? Your call. I call them POIs. I got a couple POIs here, huh? Where the graph changed concavity. True? So let's do a couple problems where we just blast it out from start to finish. And we find everything like this. See this graph function I got here? Let's find where that function's increasing and decreasing. Let's find where that function's concave up and where that function's concave down. Let's find all the points of inflection. All the points, if there are any. Because you go, does there have to be a point of inflection? No. Everyone, think of the parabola like this. It's always concave up. So it never changes what? Concavity. True? But if you go to x cubed, I think you'll find one point of inflection on x cubed.
0.
I want to see very much. Oh gosh. What do y'all think? X cubed does the what? The snake. Can anybody see the one point of inflection on that graph?
0.
Oh look, concave down, stop. And right there it changed to what? A concave up. So right there when you got a little point of that function, point of inflection. But some functions don't have points of inflection, do they?
You know,
You think of y equals x squared?
most likely in sine and cosine function, that's where you have more.
Oh yeah. My goodness, sine and cosine functions, they're always changing what? Concave up, concave down, concave up, right? Someone good with this stuff? Yeah? So, you ready to blast through this thing?
Yep.
Alright. We should make a big list. Where's f increasing? So we're going to have to list the interval. Where's f decreasing? Alright. Let's find local max. At x equal to blank, local max is blank. At x equal to blank, local min is blank. Now in here we're going to put integrals. Where is f increasing? Notice I didn't say f prime increasing. I said where is f increasing, okay? We'll put some intervals down on that. We'll find all this. Now everything I wrote on the board so far. Local max, local mins, and we won't list the critical points, but can we at least discuss it? Maybe in your notes you'll say these are critical points. Okay? All this is done with which derivative? First derivative or second derivative? First derivative. So would you in your notes? Just make a note. See all the stuff I've written on the board? You go, what's going to determine this? How am I going to find these? You're going to find all these with the first derivative. Cool? All this stuff. So they're like, all right, man, I'm going to get all this stuff with the what? I'm going to use f prime to get this thing. Somehow, some way. Now, under this, let me put some other things. And when I say we list any points of inflection, can I just put poise? Poi for point of inflection, or feel free to write IP for inflection point. We'll see if we can find any of those. We're going to put the interval where the graph is, the function is concave up. and then release the interval where the function is concave down. But I put a big wall, because you know what we're gonna use to find this stuff? Not the first derivative, we're gonna find the second derivative. You go, why? Because if you recall the definition of concavity, we said O is where the first derivative was increasing. And it was where the first derivative was decreasing, right?
Okay,
So
yeah.
we're gonna look at, not first derivative, the determinist stuff, we're gonna look at
Second.
second derivative. So yeah, let me just go, here, I'll get this out of the way. And don't worry, I'm gonna do a couple problems like this today. I think one with the graph stuff. So that's what we'll do. But always keep in mind, this junk up here, where's the function ingredient? Where's the function? Where's the max? Where's the min? First derivative. Alright. Oh, where are the point of inflections? Where's it concave up? Where's it concave down? I'm looking at what? Second derivative. Cool. Now, some students in this classroom, they've taken calc before and they're sitting there going, you know, you could actually use second derivative to find max and mins, and they are correct. So we can talk about that later. Alright, you can actually use second derivative to help you determine, but you still have to know the critical points. And try, plus, don't you agree, to get the second derivative, you always gotta move through which derivative? First derivative, there's no shortcut. You can't get around the first derivative to get the second derivative. So if we're gonna do the first derivative anyways, might as well find this stuff out. Sound good? Alright, let's start out. Everyone, let's find they call this the first derivative test. This first derivative test will help us determine all this stuff. Let's use the first derivative test. Alright, the first derivative test, I get 3x squared minus 1.
3.
Now, what should I do with this in the first derivative test? I should set this equal to something.
0.
Brilliant. So that's what we're going to do. With the first derivative test, let's always take the first derivative and set it equal to 0 and determine where it equals 0. And I'll put whisper, parentheses, or where it does not exist. So if you got some crazy word function, you know, with a fraction and there's an x in the denominator, you can also determine where it doesn't exist. Because sometimes maximins could occur there, but that's not every case. This is a simple polynomial. So I'll set this equal to 0, and our factoring skills come into play. How are you with factoring?
The 3.
All right, I heard it. Bella says you can factor out of what?
3.
3. Now what am I left?
1.
That's called a difference of perfect squares. How do you factor a difference of perfect squares?
X.
X minus 1 and
X plus 1.
x plus. I think today, every function we're going to deal with, at least today, you'll be able to factor. You won't have any trouble factoring. But you could say the more complicated ones, maybe I have to do quadratic formula or something like that. But yeah, pretty simple so far. Now, yeah, you sure can. Josephine, very good. Be careful when that word critical points. I don't see 3 critical points. I only see 2. Sometimes students mistakenly think, is that a critical point? No, that's nothing. Let that 3 hang there. Your critical points are points such that x, right? First derivative equals at certain x values. So it looks like we're getting how many critical points?
2.
2. One of them's where? And the other one? Now I do want to say something about critical points. Sometimes a critical point actually could be a point of inflection. You never know until you keep working it out. So critical points definitely find your max and mins. They definitely do. But sometimes, I didn't want you to think if you had like 5 critical points, that you're like, okay, these 5 critical points, they all got to be max and mins. You know, one of them might be the point of inflection or something. We'll find out as we keep working through the math, okay? Now, what do I do next? I know at x equal to 1, x equal to 9. This is called the first derivative test, if you wanted to write that down, what we're going to apply. After I find these critical points, I want everyone in here to make a number line. You might say, should I draw the curve? We all have knowledge of x cubed graphs. What do they look like? That's not a bad idea if you explore this picture, clearer beforehand, but sometimes the function's so crazy, we don't have a sense of what the image really looks like, But this always works. Make a number line. And on your number line, put your critical points. So make sure, hey, Josephine, I have to do this from lowest to highest. So which one of these is lower?
-1.
So I'm putting -1 to the left and 1 to the right because it is a number line. There's my critical points, true? We're trying to find these numbers, if there are any, and these numbers. All right, now, let's go back to this definition. We said a function is increasing as long as its first derivative is what?
Positive.
Positive. So that's what we're gonna do. This is f prime, right there, equal to 0. This was f prime, equal to 0. So I want you to think, you and I are gonna plug some points, some test points. But I have to be so very careful, and you have to be so very careful when we pick test points, we plug it into the right thing. This is called what test? The first derivative test? Then I'm going to pick some test points in these intervals, and I'm plugging them into the first derivative, okay? And if the first derivative is positive, the function's increasing. If the first derivative is negative, the function's what? Decreasing. So, look, I'm going to put an f prime here. Maybe I'll rewrite what f prime was so I don't forget. What was f prime? It was 3 times a what? Which one do you think is going to be the easiest to plug numbers in? I think this one. It's up to you. You might say that one, but I like that one. It doesn't matter. I'm just going to write it again, and I'm going to put a box around this. Because I want to make sure I'm putting my test points into what? The right thing. This is called the first derivative test. And it's going to give us all those answers there. Now, who's got an easy test point between -1 and 1? 0. Where do I plug it? You plug it in the no, don't plug in the original. Plug it into the what? First derivative. I don't care about the number, I care about the sign.
Sorry.
Is it positive or negative? It's negative. Now I don't want to rush you. This is you plugging this stuff in. You might have plugged it in here, you might have found it easier. 3 times 0 minus 3. Yep, use your calculators if you have to. Let it go. Let me just see. 3 times 0 minus 3. Is that positive or negative? Okay. Hey, keep in mind, a lot of times these alternate. I can't say it's 100% of the time, but a lot of times, if that's minus, you know how graphs behave. They what? Don't they do this? They do this little wave thing. So if it was decrease, it's probably going to what next? Increase. But every once in a while, you get a goofy function that does like a minus, then the minus around a critical point. So just be careful.
Can you